Hello everyone, today we're going to look at two-step experiments. So imagine you have two playing cards, one king and one queen. Now you can pick up these two cards by either picking up the king first and then the queen, or you can pick up the queen first and then the king. But what happens if you have three cards? How many different ways would you be able to do this? Or if you had four cards? Let's investigate. We're going to use a tree diagram because in probability, it is very important to consider the ways in which an outcome can be achieved. This is especially important when several events are happening together, and a tree diagram is useful for showing all combinations of the events that can happen. Imagine you have three cards, Jack, Queen, King. We're going to choose one, then put it back, and then we're going to choose a second card. What combination could we get overall? So for the first card, we're going to draw a tree diagram. We're going to start it off with three sections because we can pick three cards. And in our second card, we're going to consider, well, if I pick the Jack, what happens next? I can pick the Jack, the Queen, or the King again. If I pick the Queen, what happens in my second card? I could do the same. And I can do the same for the third card. So how many different combinations am I going to get? These are the outcomes. So I can have Jack, 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 Queen, etc., etc., all the combinations. So it's like following the trail of the tree diagram. So there are 9 possible combinations of events in this situation. What is the probability we choose at least one Jack? What does that mean? That means we're going to look at every single outcome that has the word Jack in there. So there are 9 outcomes here and 5 of them contained Jacks. So therefore we have the probability of picking at least one Jack is 5 out of 9. What is the probability we choose the same card twice? So now we're going to look for the ones that have the same card. So Jack, Jack, Queen, Queen, King, King. So our answer is going to be 3 possibilities out of 9, which is 3 out of 9. And we simplify this always, and it's 1 over 3. Now, along with tree diagrams, you also have to learn to draw array tables. This is an array table. So the first card or the first event goes this side and the second event goes over there. So in the first card we can pick Jack, Queen, King, and in the second event we can also pick Jack, Queen, King. And we fill in the table with all the outcomes like so. So I've color coordinated to help you see that this is the first card that relates to this one here. And then we have Jack, Jack, we have Jack, Queen, we have Jack, King, and then therefore the next 3, which comes from Queen and these 3 options are here, and then that King, the first card, is here, and then my second cards, these 3, give me those outcomes. Let's have a moment and see what is the chances of picking, let's say, Jack, Jack, this one here. What is the probability of picking that? Well, there's 1 outcome out of 9, so that is 1 out of 9. But is there another way to work this out? What's a useful way that we can work that out? We look at the first event. There's 1 Jack out of 3. So the chances of getting a Jack is 1/3. We look at the second event. The probability of getting Jack out of these 3 is also 1/3. So how do we get 1 over 9? So we need a Jack and a Jack. What do we do with 1/3 and 1/3? Does this and means multiply or addition? So it means multiply, because when we multiply these two, we're going to get 1 over 9. Now remember that when we follow a tree diagram, we say we want this and something else, we multiply. But when we look at the outcomes and we want Jack or Jack, or let's say doubles before, King of King or that, when we say or, we means plus. So just a recap from last lesson, the 2 words were intersect and union. Intersect has a symbol, it means and, it means that it has to satisfy both conditions, or in other words, it's the overlap. So for example, before we wanted 2 jacks, we want 1 jack and the other jack. Whereas the word union has a symbol and it means or. So the outcomes, when we wanted this outcome or the other outcome. So it can satisfy any conditions. So we are adding them up for this one. So it's intersect when we want this and that. When we're being very particular, it's multiplying. And when we want or, we're adding. A good way to think about this is, let's say, what are the chances of winning the lottery today and tomorrow? Well, and means it's really hard to win the lottery both days. So we're multiplying the fractions, because when you multiply fractions together, they become a smaller chance, a smaller number. What is chances of winning the lottery today or tomorrow? We're increasing our chances because we can win this day or the next day. So if we're increasing the chances, what do we do to fractions? We add them. So then our total fraction becomes a bigger value. So or means plus and means multiply. Let's look at this array table and see if we can answer the same questions before using just the table. So what is the chances we choose at least 1 jack? So we look at the table and we look for things that have at least 1 jack. So this is 1 jack at least, because it has 2 jacks. This is jack queen, this is jack king, this is queen jack, this is king jack. Remember, this is the first card. That's why I'm reading it as queen jack here, but jack queen there. So those are the ones we want. So we want this, or this, or this, or this, or this. So what does or mean again? We're adding them. So we want 1 over 9, or 1 over 9, or 1 over 9. And I'm just writing them all out, and we get 5 over 9, just like we did before. Let's have a look at a scenario where we don't put things back without replacement. So before, in the first event, we took a card and then we put it back, and we took another, we took the second card. In this event, what happens if we keep the card? What would happen? So when we draw the tree diagram, we will have, in our first event, or the first card we pick, we have the choice of 3. So jack, queen, or king. So the probability of picking that card is 1 out of 3. Now, but in the second event, we only have queen and king if we pick the jack. And if we pick the queen, we only have king, jack or king. And if we pick the king, we only have jack or queen. So the probability for these ones would be different. It will be only a half, because we have now 2 choices. So a half, a half, a half, a half, a half. So now we can have 1, 2, 3, 4, 5, 6 outcomes. So any of these would be having the equal opportunity of 1/6. But remembering from before, if we follow the tree diagram, we must multiply. So any of these can be worked out by multiplying this and this, which is equal to 1/6, just like we predicted. So looking at the array table, we don't have double jacks. It's impossible because we've kept the card. We didn't put it back to get a second one. We don't have double queens, and we don't have double kings. So we have 6 outcomes left, and they are all 1/6 in probability. What is the probability of ending with the queen and the king? So queen and king is here, and king and queen is there. So we can see from the number of outcome is 2 out of 6, or in other words, 1/3. Or if we look at over the array table, queen and king will be queen and king here, and king and queen here. And we could add them up to get the same solution. What is the probability of choosing the king then the queen? Is this the same question? No, because we don't want queen or king. We just want the king first and the queen. So the king first and then the queen second. So we only have 1/6. We're fussy at this time. So the probability of getting that solution is a lot smaller, 1 out of the 6. Let's look at another example. In a bag, there are 12 blue and 8 red sweets. Draw a tree diagram to show all possible outcomes when 2 sweets are drawn out and are replaced. So in our first pick, we have 12 blue and 8 red. So we're going to put blue and red as our options, and then we're going to work out the probability. So for blue, we have 12 out of the total. The total is by adding all the sweets together. 12 plus 8 is 20, so we have 20 in total. So for blue, we have 12 out of 20 as the probability, and for red, we're going to have 8 out of 20. So that's the first pick. Now, if we're putting the lolly back, then in our second pick, it's going to be exactly the same. How do we write probability? We write P with an open bracket. So P of B and B means the probability of picking blue and blue. So we're going to write down the 4 outcomes. And now let's calculate the probability of each of these outcomes. So remember, when we go down the lines, we always multiply. So the probability of getting blue and blue would be that times that. And we always simplify. And we can do that for every single section, every single outcome. So these are the 4 probabilities of our outcome. These also add up to 1, and it makes sense because all the probabilities, all the possible outcomes have to add up to 100%. Whenever you draw a tree diagram with the probabilities, you can check your answers by adding it, and if it doesn't add up to 1, you know that you made a mistake somewhere. So let's move the probability there and then answer some questions. What is the probability of picking 2 sweets of the same color? So we're talking about same color, that or that. So red and red or blue and blue. So let's write it out. Probability of blue and blue plus probability of red and red. Now you might wonder, why am I saying plus this time? Because we're saying blue and blue or red and red. That's what we want, blue and blue or red and red. So it's a plus. So the probability of blue and blue, we worked it out. And the red, we just add it together. 9 plus 4 is 13 out of 25. Let's look at another question. What is the probability of picking 2 sweets that are different in colors? So now we want the other 2 answers, blue and red or red and blue. So plus for all. So now we have 6 over 25 and 6 over 25 from the table. Add it up together, we get 12 out of 25. Next question. Same question. We can also figure out that when you look at these, that is the same as saying everything minus these 2, which means everything is 1 minus the same colors. So 1 minus 4 plus 9 is 13 over 25. And that's going to give us the same answer as adding those 2 together, 12 over 25. This is really handy, and this goes back to the first lesson of probability when we learned the word complement with an E, complement, because the probability of the chance of getting A and together with the chance of getting the complement of A means everything. So that means that if we wanted to work out the chances of A, that we can take everything, take away the complement of A, which we have done in this example. Let's look at the next example. A wallet contains 2 gold coins and 8 silver coins. A coin picked at random and then replaced. Sorry, coin is picked at random and put back. A second coin is picked. Draw a probability tree diagram and calculate the probability of picking 2 silver coins. So we've got 2 gold coins and 8 silver coins. So we have 10 coins all together. So we got gold and silver. Pause the video here and give it a go yourself at drawing the tree diagram, and then continue after to check your answers. So we've got gold and silver, and we have the probabilities over there. And we're going to write down the outcome that we want and just work on that outcome, which is 2 silver coins, silver and silver. So we want to go down the tree diagram, we multiply. So now we have 8 over 10 times 8 over 10 is 64 over 100 equals 16 over 25. If a matchbox is dropped onto a table, experiments show that it lands on the edge with a chance of 0.2. Edge. Matthew drops 2 boxes. Complete the tree diagram. So this is the first drop. This must be the second drop. And we have edge, so the opposite of that will be not edge. And remember, they have to add to 1. So if edge is equal to 0.2, then the not edge, oops, I can't spell anymore, has to add up to 1. So the not edge will be 0.8. I'm going to fill in the table. The probability doesn't change in the second box because we haven't kept anything or changed anything. Calculate the probability of exactly one of the matchbox landing on its edge. So we want edge and not edge, or we want not edge and edge because we said exactly one of them being edge, not both. And remember, going down the tree diagram, we multiply. So recap, edge and not edge, or not edge and not edge and edge. So the and is the times and or is the plus. And then chucking it in your calculator, it gives you 0.32. Next question. What is the probability of either or both not landing on the edges? Well, either means we don't want the edge for the first one, or we don't want the edge for the second one, or we don't want both not edges. Okay, or an easier way would be to realize that we don't want edge, but we want every other combination. So edge, not edge, not edge, edge, and not edge, not edge. So we want these three. What does that mean? We want everything except for that. So everything minus that. So let's do that instead. There's less mathematical calculations and therefore room for less error. So we know that edge is 0.2 times 0.2 as we go down the tree diagram, which is 0.04. Be very careful with your decimal points. This is 1 decimal point, 2 decimal points. Therefore, your answer has 2 decimal points. So 1 minus that is equal to 0.96. And it makes sense because there's a lot more of these than that one option. All right, that's it from me today. Bye.